Welcome back and welcome to Section 5, Lists, Maps and Sets. In Section 5 we're going to take a look at some more data structures and data processing. So welcome to Video 1, Data Structures, Interfaces and Concrete Implementations. So this is really just an extension of what we were talking about in the previous section. In the previous section we were focusing predominantly on lists. In this video we're going to take a look at some of the other data structures available to us as well in Java 9. So remember, Java supports a number of data structure interfaces, each of which have a number of concrete implementations. So in the previous section, we looked at the list interface, and we also looked at the ArrayList implementation of the list interface. And we discussed how there are a number of different implementations of a number of different data structure type interfaces. Now recall that an interface is just a simple definition of the methods that an object must provide. The most common interfaces are set, list, queue, double-ended queue, and map. Each of these can be implemented in different ways, but each of those must also conform to the parent interface. So for example, any list implementation must be an ordered collection that supports methods like add, get, set, and remove. And all of these interfaces are generic. That is, they support any object type you want to put in them at definition time. So in the previous section, we showed an example where we created a list of integers, and another example where we could create a list of cars, where cars being the class that we had written ourselves. And we also looked how when we created that list, the generic implementation in Java actually overrides or customizes the add and remove methods of those implementations, such that a list of integers, when we call the add method, we can only supply an integer. We can't then supply a car or a double. So this allows us to be very type safe and very explicit about the formats of the data structures that we're creating, because we're defining the type of data that we're going to put into our data structure at instantiation time. So let's go and take a look at the interfaces. So firstly, we have a set. And a set is a collection of unique elements, and this actually mimics the mathematical concept of a set. And a set stipulates that everything in it must be unique, so you can only insert an object once. And a set actually only stipulates methods for adding elements and then checking if they exist. So you can't really retrieve an element directly without an iterator. There's no concept of a list type interface with a set. There's no concept by definition of ordering, for example. It's just a bucket of unique elements. So there's no guarantee around order, although some implementations do actually support this. And common implementations of set are hash set, tree set, and linked hash set. And the most common one, to be honest, that you're likely to use is hash set. It's the most high performance implementation. What happens is when you insert the object into the set, a hash is taken of that object, and the set maintains the hash. It's a low collision hash. So when you go to try and insert a new element, the set will then hash the new element and compare it against a list of hashes that it's already stored. And this is generally useful for maintaining a collection of elements in order to determine the uniqueness of something new. So for example, let's say you implemented a sign-in page. You might store username or email address in a set because you want to know that the new email address that someone's providing when they register is actually unique. Next, we have a list, and of course this is something we've already talked about in the previous section and seen a few examples of, but a list is just an ordered collection of elements, and I want you to think of it a little bit like a shopping list. With a shopping list, you just essentially add new things on the bottom. Now, you can add new elements to a list in place, but that actually overwrites something that's already there. So imagine a shopping list. If the third item was bread, you can't add a new item on top of that because you've already got items below it. You'd have to cross bread out and write something else like eggs, for example. And then if you wanted to write bread back on the list, you'd have to add it in at the bottom again. That's kind of how a list works. Again, as with a shopping list, it may contain duplicates. There's no stipulation around uniqueness of a list, but it's really powerful in terms of retrieval mechanism because you get useful features like positional access, like I can get the fifth element of my list. I can insert anywhere in the list. As I was just saying, you can insert into the fifth element and overwrite anything that was there. You can search through a list. You can iterate through a list. And you can always also do range viewing, which is essentially where you say, get me everything between the 4th and the 10th element in my list, for example. Now, the most common implementation of the list interface is the ArrayList. LinkedList is also useful, but it's much slower for reads, although it is a little bit faster for writes. And as we discussed previously, it's typically much better to use a list than an array. So just looking at array lists versus linked lists, an array list is implemented a little bit like a dynamic array. That is, its size grows as needed. So you can just keep inserting stuff into it as and when you need, and Java will clean up for you automatically afterwards. Conversely, a linked list is essentially just implemented as a double linked list. So this means it's faster for add and remove operations, much slower for gets and sets. One of the benefits of the linked list implementation is that it actually also implements the queue interface. So this means you get methods like offer, peek, and poll. Now, this is not something we're going to be demonstrating in this tutorial. It's a little bit outside of the scope. But if you want to maintain a queue of work, this is very helpful, because you can poll the list for new items, you can peek at the list to see if there's something there, you can offer something onto the list, and you can also pop elements off of the list to do work on them. To be honest though, if you're using a list, chances are you want something that looks and behaves like a list, and in most cases an array list is the best performing choice. Although a linked list is, as I said, marginally faster for writes, about 30%, I think, something like that, it's almost 6 times slower for reads, which is a substantial penalty to pay.